So let me start by reminding you what I was doing last time. So last time I essentially proved the localization axiom for the category of foliated motifs. But this was somehow it was a restricted version, in the sense that it does not a priori hold for arbitrary closed immersion. So we had to restrict to this, I think, so-called admissible closed immersion. And so as a consequence of this was some amount of work, one deduced that there is a working formalism of the sixth operation in the context of foliated motifs. And so, I mean, essentially, one could just fix. So maybe I just write it quickly. So what one can do is one fix a base, and one look at basic SE foliation, something this form. Associated to a finite presentation S schemes. And maybe let's say also, I mean, just for simplicity, just also say finite type and smooth also. So in this context, I think essentially one has a good form. Of course, one has to pay some care. I mean, for instance, when you consider Cartesian squares, you don't want that the fiber product is singular. But yeah, modulo these kind of issues, there is a working formalism like this. And so I just want to record one consequence of this, which is what I need. So let's write it as a corollary. So this is what I was calling the motivic Grothendieck-Verdet duality. So we have SE as before, so base, and then we write P for some morphism, which is smooth and projective. So then we have the direct image functor, which I compute, let's say, for the Psi-Nislevich topology. Right, so this goes from theory of foliated motifs for the Psi-Nislevich over XE to the same thing over SE. Okay, so we have this functor, and and so the corollary say the following. So there is a natural isomorphism of operations between this guy R Psi-Nislevich P star and L P sharp. So remember, this is the left adjoint to P upper star, composed with com minus 1. Okay, so this is yeah. All right. So let's go back to. So let me now describe the application of this to. This is 3.4. So the application to the spectrum representing the ramp cohomology. Application. So again, let me remind you what we were. So in studying this guy here, so we had, so we have constructed a map from omega, morphism of spectra, to this. I think let me just be sure. Yeah. So. Pi dollar star. And then we have this suspension spectrum of some pre-sheaf, and this was made made fibrant for the CFT topology. So we had this morphism, and I said that somehow to for the proof of the conservativity, it will be important somehow to lower the contribution. So in this formula here, you see two things in some sense. So you see motivic cohomology coming from this part, from the infinite suspension spectrum, and then there is the ramp cohomology, which is somehow coming from here. And so one important step in the story is somehow to lower the contribution of the ramp cohomology. And so we will do this by replacing CFT by some weaker topology, and then somehow again putting CFT, but somehow after applying direct image. Right? So what I want to do, so the goal is to somehow replace this by this thing. C et al. And in fact, I can even do Sinisnevich, fibrant, and then CFT fibrant. And so I hope you see that somehow there is some improvement when doing this. Okay, so yeah, the idea is that so here you see more the ramp cohomology because you apply somehow this replacement on larger schemes, right? So here you have E bar times A, and here you apply topology, but somehow only on the factor A. Okay, so you get less the ramp cohomology in some sense. So this is what I want to explain, and this is somehow essentially a consequence of this corollary. So here's a theorem which is a consequence of this corollary. So let's keep the same notation as above. Same situation, same notation. So then the claim is that the functor are Snesnevich Pilauer star preserve stable A1 CFT local equivalences. Okay, so and of course to prove this, so I rather will work with this functor here, so which is possible since I have this isomorphism. So here's the proof. So enough to do it for LP lower sharp composed with a Thom space. Okay, Thom minus 1. P. Now let's maybe first look at this guy. So we know that this is an equivalence. And so enough to show that its inverse, Thom omega, preserve local equivalences. But then this guy here is something like, you can write it as Q lower sharp, T lower star. So Q will be the projection of the vector space, vector boundary space to omega p. This is the 0 section. Then you remark that we know that this guy preserved local equivalences. So this is fine. This guy preserved CFT local equivalences. I think I proved this last time. And so we are left to deal with this guy, which is an L, which is of the same form of this guy. So at the end, you need to treat, and then you need to show that F lower sharp preserve stable A1 CFT equivalences. And I mean, I should also say that stable A1, this is not really a problem. The main issue is to really to show that an CFT local equivalence will go to something invertible. Okay. And so now, I mean, this follows. So this follows. I mean, there are two ways to see this. So there is the quick way. So you say that F lower sharp is left equivalent for the stable A1 CFT local model structure. And then you use the fact that cofibration of this localized model structure are exactly the cofibration of the global model structure. Okay, so this is the quick way. The more concrete way is to do the following. More concretely, so we know that the CFT local equivalences, they are generated by hypercovers. So we take a hypercover. So that YG to YG minus 1 be CFT hypercover of some scheme over X. So of y minus 1, g minus 1 over xe. And so we want to see that this induces, so that when I apply f lower sharp to this, I get something which is also an CFT local equivalence. But this is clear because lower sharp, what does it do? It just takes the same thing and forget the structural morphism to xe, or rather compose it with the morphism f. Okay, so there is nothing to prove. So from this one gets immediately the following corollary, which is very close to what you want, but we will see that. Yeah. So what is the corollary is, so again, let's keep the same notation as before, and let's now take E, a T spectrum. E, a T spectrum. Over xe. So then there exists, then the natural, there exists a quasi-isomorphism, level-wise quasi-isomorphism between, so you take E, you make it A1 Psi stably fibrant. You apply to it P lower star, and then you repeat again. So you make it now A1 Psi FT stably fibrant. And this is the same as just applying P lower star to E made A1 CFT stably fibrant. Okay, so just quickly, why does this follow from the previous statement? The map from E, okay, the map from E A1 Psi Nesnevich and so on to E A1 CFT. This is, by definition, this is a stable A1 CFT local equivalence. Between fibrant Psi-Nesnevich objects. So if I apply to this P lower star, the previous theorem will tell me that this morphism of spectra is also a stable A1 CFT local equivalence. Okay, because I know that P lower star preserves these kind of maps. Okay. Now, if I have now this guy here is still A1 CFT fibrant, stably fibrant, because also P lower star preserve fibrant objects. Okay, this is but then if I so I have an equivalence from something to something which is fibrant. So this means that this is a fibrant replacement of this. Okay, so then we get what you want. Okay, so now I come to a remark about. Okay, so. Okay, so this corollary applies to the situation you are interested in, namely to the morphism rho, which is it's a morphism of diagrams, but simply because this morphism of diagram is given by smooth and projective morphism, right? Projection to the first. So this is a product of P1s times A projecting to A. Okay, this is a proper morphism, and therefore direct image commute. I mean, we have this property for rho lower star, and so. What we get that, unfortunately it's not anymore on the blackboard, but we get what we want. So we get what we want, except that, so instead of tau fibrant replacement for tau in Psi-Nisnevich or Psi ft. So instead of tau fibrant, we get this more complicated things: A1 tau stably fibrant. Okay. Now this is not a problem if we, I mean, if for tau in. So for tau Psi-Nisnevich, this is really not a problem, because then we know somehow how to write down a fibrant replacement like this from one like this. Okay, we have seen it last time, some previous time. So this is given by singular complex. Maybe you have to make it. You have to also make the spectrum stable. So there is a lambda infinity, and this is applied to a tau fibrant replacement. But this is not. But this is only for tau equal Psi-Nisnevich. And so what I'm trying to say here is that so if we really want to remove these two things, stability and A1, it's possible to do it. In a manageable way, in a way that we can understand, just putting these two operation before, so at the beginning of. But this only can be done, unfortunately, for this topology. It does not work for that one, and it's again the same reason. It's because this topology doesn't have finite cohomological dimensions, so we don't have a model for this kind of fibrant replacement, which that we can understand. And so this is actually a true problem, and then one has to find a way to fix this. So I will not explain how this is done. I will just maybe give you some hint what one has to do to improve the situation. Okay, so I'll just describe quickly a fix to this problem. So again, make a mark. So to fix the issue which is caused by, so with infinite cohomological dimension of this topology. So one has to do something, and so one works. So in somehow, of course, it's an artificial fix, but it actually can be useful maybe in different contexts. So to do this, one works systematically with end object, and here so it will be end complexes of presheaves on smooth foliation, and so somehow so one has to put model structure on end complexes, and so the main point is the following. So instead of taking somehow end complexes up to local equivalences for these topologies, so we make a boost field localization with respect to hypercovers, but we think about the hypercovers something like this. And so we declare that. So we declare that this is a weak equivalence, but we do this, and so we consider this map as a morphism of end complexes, but somehow yes. So these are considered as end complexes in the obvious manner. So what do we gain by doing this? Let me say it orally. So I mean the problem when you do this in the category of complexes of presheaves is that this guy here is not compact. So I mean, this is a compact object in the category of presheaves. You know what is a compact object, right? So it's but this is not a compact object, and this is somehow what causes. So we are making a boost field localization with respect to objects which are not compact, and this is what causes this infinite cohomological dimension problem. But if we do it in this manner, so we think about this as an int, as a morphism of int complexes, then essentially by construction everything here is compact, okay? Because a single complex considered as an int complex is a compact object. And so somehow we resolve the problem like this. Of course, one has to check many things. One has to check that, for instance, that you can still prove the localization axiom in this setting. And so it's, one has to do this. But it's possible to do it, and somehow this gives what we want at the end. So let me just write down the theorem that we need to continue. Okay, so we get the following statement. There exists a morphism of T spectra on smooth foliation over K. Maybe you have to restrict to Noetherian thing. And this morphism goes from the thing that we want to understand to this singular A1 composed with lambda infinity, composed with totalization in theta bar of this rho lower star computed computed with the Seattle topology, maybe Nisnevich, sorry, and then the whole thing made vibrant. Okay, so this is what we need to remember for the remaining of the course. Any question about this? So do you know what is lambda infinity? I don't remember if I described this. Should I remember? Huh?
Yeah, I think you could say the definition again.
Okay, so let me do it quickly. So, yeah, maybe reminder. So this lambda infinity. So it's an underfunctor of T spectra. So it takes a spectrum and gives you a spectrum, which turns a T spectrum into one which is an omega spectrum, which is stable. So it's an operation of similar nature as, for instance, SGA1. SGA1 turns something into an A1 local complex. This is also the same. It makes it stable, and it's not, for the moment, it's not so important to tell you what is this, but it's actually quite easy. So maybe I say it. So lambda infinity is given by the colimit of finite version lambda n, and lambda n is of a spectrum so I think is given by internal home. So it's like a loop space from T tensor with n to E, and I think there is an S minus composed n time. So this is a formula for lambda n. This is the operation of shifting the spectrum. So I think so S minus of E, I think in degree n, will be given by E n plus 1. I think so in degree 0 it should be, yeah. Okay, so you shift the spectrum, and you apply loop space in each degree, and then there are morphisms between these lambda n, which are induced by the assembly map. Okay, you can write down morphism between them, and you pass through the colimit, and this somehow makes your spectrum an omega spectrum. Okay. So the point that now everything is, I mean, all these things here are quite concrete. We still have to understand a bit this, and especially understanding this part here. Okay, so this is the end of chapter 3. It's so now today I will do chapter 4. which is about some computations of foliated cohomology. And I can say the goal. What is the goal of this chapter? So the goal is to compute the restriction of the thing that appears here, namely, so yeah, I give a name to this. So I want to compute. So this is a spectrum. I want to compute this spectrum. Actually, yeah. Oh, I forget something here. Good. So I forget to put up here also. All right. So I want to compute this spectrum here, or the restriction of this to some nice foliations in of course in the category where this is living. So it's in this thing. Nice would mean, for instance, example smooth variety. Endowed with a coarse foliation, or maybe a completion of smooth variety, some closed subset. And so computing this means exactly computing. I mean, I think the most difficult part of this formula is really to understand this fiber replacement, and this is exactly also understanding the foliated cohomology of a nice foliation with value in this complex of presheaves. Okay, and so this is the goal of this chapter, to try to say something meaningful about this. And so I can tell you where we are heading. So we really want to somehow now we want to get rid of foliation at the end. So somehow the goal of this lecture and the next one will be to somehow to understand the restriction of this spectrum to smooth varieties in a way which does not make any reference to foliation anymore. Okay, so I want to get a purely algebraic, if you want, formula which computes the right hand side. Okay. So this will be done in 2 steps, maybe, or 3 steps, and today will be one of these steps. All right, so this is actually a quite technical story, and so I'll try to make it agreeable as I can, but I don't know. So, and I will be, of course, missing many details. So, I just want to give you somehow an impression of what's going on here. So, to do this, we need some preliminaries, and an important notion is the notion of malleable presheaf. Complexes of presheaf. Okay, so start with the notation. So I'll introduce a class of objects. So notation. So I'll denote by H the class of pro object in the category of augmented semi-simplicial foliations. Y dot G dot, which are of the form which can be written, which are of the form so you start with a semi-simplicial foliation. So x dot will be over f dot, and then you what you do, you look at the generic. So you pass the generic points. Of course, assume that you can do this, and then you add some variables, formal variables. Right, so you pick a system of indeterminates. You make the formal power series of this. You add also another dimension, but now it's not formal, it's just polynomials. And then you pass again to generic points, and you start again. You add formal variables, and so on. Of course, a finitely many number of time. Okay, so at the end, so these things will be. I should say the important condition is that with x dot f dot going to x minus 1 an ft so a generic hypercover. A generic hyper. I think I defined this before. I can repeat this if you want. Okay, it's not so important, so maybe. Okay, so I should mention that. So these guys are really. I mean, you should think about them as pro object, and the limit will be given by just points. So in each degree, this is the spectrum of some big differential field. Okay. So it's really like a co-simplicial differential field. But somehow we want also to remember the pro structure. Okay, and this is H, and H prime is, so we also denote by H prime. This is a slight enlargement of H, consisting of base change like this. You take one of these, you find a product over 1 minus 1 with some v. Like this, and where v minus 1 to y minus 1 is eta. Okay, so these are just two classes of objects. Let me just say one fact about this, which will maybe somehow explain why this is introduced. So this has a nice stability property. So here's a fact. So if you start with an object in H prime, and you give yourself, I think, some variables, you look at this thing. So maybe I should say, I mean, I hope you understand what I mean by this symbol. Yeah. So this is a pro object. When you do this, you do it level wise. I mean, okay. So anyway, so we can look at this. We can take a point in y-1. Okay. Right. So then the following is true. So that there are two claims. First, so maybe before. So then let's define yn for every integer to be the generic point or generic points. There might be several of them. So we take the union of the generic points of the pre-image of y-1 in yn. Okay, so in this manner we get we get again a semi-simplicial object. So the claim is the following. So y dot over G, it still belongs to H prime, and also if you complete y dot with respect to the small point, again over G, this is isomorphic non-canonically to something of this form. Okay. All right. And somehow this is, I mean, you could understand this as really the smallest class having these two properties. Okay, for which these two properties hold. Okay, so now we come to the definition of malleable pre-sheaves. So I fix an integer n, and let k be a complex of pre-sheaves on foliation. I don't want to be precise here, so it could be so there are different category of foliation that you could consider. So let's just say on foliation, on smooth foliation. Or even, I mean, maybe not even smooth, just on foliations. It could be, for instance, on the small site of a foliation, small FT site. Okay, so we say that K is n malleable if psi ft psi étal fibrant replacement G of K satisfies the following condition. And if it is true for one, then it will be actually true for all of them. So what is the condition? The condition is the following. So first, satisfies the following for every data as follow. So there will be 4 items, and something should be true for these items. Actually, 3 items. So we start by fixing an object of this H prime. Then we also fix some system of variables, S and T, and we ask that the cardinality of number of variables is less than n. And then we take a relative étal hypercover, whatever this means, it's not so important, V to y with these variables. Okay, and we asked that actually V belongs to the site where K is defined. And then the conclusion is that then we want that the total space, total complex of plus of the augmented complex, which is given by G evaluated at V, to be acyclic. Okay, so I mean, it's not very. I mean, it might look a bit weird, the definition, but actually, it's something really kind of natural. So if you have, so the point that if you have, so if G is fibrant for some topology, and this is a hypercover, then this condition is true, right? So if you take something fibrant for a topology, you evaluate at the hypercover, you take the tot plus, you get something acyclic. Okay? And so the point here is that these guys, they are not hypercovers for some topology, not even generic hypercovers. But somehow we want to think about them as hypercovers. And so we look at complexes for which that behaves as if these guys were hypercovers. Okay? Any question about this? Yeah, so the size of the system.
So the definition is for any C-étal fibrant replacement. I mean, for some implies.
Yes, if it's true for one, then it's true for all others. Okay, so and I will need two variants of this definition. So let's keep the same notation as before. So I would say that K is, so this is weakly n malleable if the same condition holds whenever S is empty. Okay, so I just take just one system of variables with this, which has less than n elements, and I ask for the same condition. Then we say that K is almost n malleable. Again, if the same holds under the extra condition, so under the following extra condition, which is so this is a condition which only exists when there is equality here. So if t plus s equal to n, we ask that the map from b minus 1 to y minus 1 t s factors through, so factors the open subset y minus 1 t. And I'll explain this in a moment. So there is a 0 here. So and 0 is so where y minus 1. This is simply y minus 1 t, where you remove the special fiber. So minus. Okay. So maybe a remark. So the condition of being almost zero malleable is empty. Okay, so simply because right, so if n is equal to 0, then this guy here is empty. So yeah, there's no condition. So this is the first. Second, so on the contrary, being zero malleable is not automatic, even if K itself is it's CFT 5. And this is because the object of H are not hypercovers. So since they are not hypercovers for the CFT topology, there is no reason for a general vibrant K to have this property. But it is but there is a good class of presheaves for which this is automatic. So, however, if K is homotopically continuous, so what is homotopically continuous? So maybe I see it in a moment. So if K is homotopically continuous, then K CFT fibrant is 0 malleable. So let me say this orally. So, for a presheaf to be continuous means that, by definition, it's a presheaf. That's whenever you have, let's say, a foliation which is written as a limit of some prosystem, then the value on this foliation is a co-limit of the values on the prosystem. This is the definition of being continuous. And homotopically continuous means that this is true on the homology of K. Okay. So if you have something like this and you make it fibrant for the topology, then it will be 0 malleable. And the reason for this, so it's a non-trivial fact, but it's easy to understand why this is true. This is true because actually every object of H or H prime, if you pass through the limit, then you can rewrite it in a different way as a limit of a different system consisting of generic hypercovers. Okay, so it's a non-trivial fact, but it's true that every element in H has this property. And so because of this, you get this fact. But even then, for such things, for instance, so for example, one malleability will not be a priori true. Okay, so it's a condition which is somehow difficult to check, and it's certainly not true in general. It's a technical condition, but I don't know. Okay, so here's an interesting fact about this definition. So we have the following theorem. So let n assume that n is bigger than 1. So assume that also that K is bounded on the left. So if K is weakly n minus 1 variable, then it is almost n malleable. And so in particular, and hence, and in particular, n minus 1 malleable. So this is maybe not so surprising that n minus 1 malleable. So that weakly n minus 1 malleable implies n minus 1 malleable. Remember the difference between weakly and plain. Is that for weakly we don't want to have this polynomial variables. We only want formal variables for weakly. So I'm saying that if we allow formal variables, then we can deduce the polynomial variables. But somehow, somehow what is really, I think, maybe, yeah, I don't know. What's more interesting is the fact that if you are n minus 1 malleable, then you are almost n malleable. If you find this, I mean, I don't know. If you find it, you can, if you want, you can forget about about the weak version. Just keep malleable and almost malleable. So I'm saying that if you have something which is n minus 1 malleable, then it will be almost n malleable. Somehow this is the interesting content of this. So I want to very quickly sketch the proof. I mean, I think the proof is a bit long, but just give you some idea of what's going on. So what do we need to check? So I will only do this implication. So I assume. Yeah, I mean, actually it's the same. So all right. So what we need to do? So we fix v dot g dot as in the definition. With the condition that t plus s equal to n. Otherwise, there's nothing to prove. If you are smaller than n, then there's nothing to prove. So we take this case, and we assume, of course, the condition that v minus 1 to y minus 1 factors through the open subset y minus. Of course, this condition implies that the same is true for every integer, right? And so in particular, so this condition implies that the dimension, the full dimension of Vn is of Vd for every d is smaller than n minus 1. Actually, it should be n minus 1. That's right. Right. So the goal is to show that. So we have this fibrant replacement, the alpha, C alpha, and we want to show that tot plus is acyclic. This is what we want to prove. Okay, so the idea is to filter. So we can filter VD. So VD, I mean, these are very nice schemes. I mean, they are excellent schemes, finite dimension. Okay, so Noetherian finite dimension. So we want to we filter these schemes by Coniveau, meaning that I'll be looking at pro open subset of VD consisting of complements of subschemes of some codimension. Okay, so we do this usual thing, and this induces a filtration on these complexes, and we look at the graded pieces. Okay, so the graded pieces are can be written as follows. So the graded pieces can be written as follows. So in degree in some so. Yeah, that will be given by direct sum over points in some v dot in some degree of codimension. Let's fix the codimension. Let's call it R. Codimension R of somehow the relative cohomology. So if you want. So this is so what we do. We complete V at the point x, and we mod out in some sense by the completion again at x, but where we remove the point. So this is just a notation for for the homotopy fiber of the map from GVX to GVX minus X. Okay? So if you want, this is cohomology was supported at the point X. Okay? So we have this thing, and so we want to show that this guy here is contractible. So now something interesting happened, so I'll try to describe this. Okay, so something interesting happened now, which is the following. So it's a fact. Okay, so this is somehow the key fact of the proof is the following. So given X in some PD of codimension R. So then there exists a unique, so how to say this? Yeah. So maybe I need to make a definition, I think, first. So let's see. So X in VD of codimension R is called primitive. So maybe this is not a fact, but definition. So it's called primitive if for every map, so for every inclusion of simplices, if for every the map VD to VD minus 1 takes X into a point of codimension smaller than R minus 1. Okay, so the schemes VD they all have the same dimension. Okay, they have dimension, I think, n minus 1. Okay, I mean, you can think about them as open subset in formal powers, so formal power series scheme of dimension n. But somehow they have the residue field of these schemes are different. Okay, so it happens often that if you take something of codimension 1, for instance, it will be dominant over by the projection. Okay. Is this? Of course, if you are dealing with finite type scheme, this never happen, right? So if you have a morphism of dimension n schemes, which is dominant, so it will be generically finite, and then somehow the codimension cannot increase. Okay, here it does. It can increase, and it does actually often. Okay. And so a point will be called primitive if somehow this happens for every projection. Said differently, it's a point which does not. So said differently, X is primitive if it is not the generic point of a pre-image of the pre-image of a codimension R point in VD minus 1. Okay, so it's somehow you cannot obtain it from lower degree. And so it turns out that this notion is well behaved. It's nice, and it gives a structure somehow on this complex. In fact, it induces a decomposition of this complex. So what we can decompose. So we can decompose the above complex by can decompose complex using primitive points. So I tell you what will be the summand corresponding to a primitive point. So if you fix x in VD primitive, what you can do, one can define a co-simplicial functor from delta prime over D. So delta prime is the category of simplices where we only allow injective maps. Okay, so I'm looking at, so an object of this category is an injective map from D to something. Okay, so whenever I have an injective map from D to something, so let's maybe call it like this, D maybe E. So I associate to this a group which is a direct sum of all points in VE codimension R mapping to X via this induced map. And then you take G of VE, Y, and so on. Okay? And then, so you are left to show that these complexes, so this is not a complex here, but this functor, as you do with semi-cosimplicial groups, you can associate to this thing a complex in a natural way, and it turns out that this complex is a direct summand of this complex here, and that this complex here is a direct sum of all these complexes that you obtain. Okay, so at the end you are left to show that this kind of complex is acyclic, and this is by some formal manipulation using, I mean, just some simplicial manipulation, you can reduce to the case of, in fact, of D equal to -1, where it's exactly given by the condition of being malleable. Okay, so this is more or less a proof. So as a corollary of this, we get this. I mean, this. It's really a non-surprising corollary that will not say anything about the proof. I'm sure you can imagine how this is obtained from the previous theorem. So again, we take an integer. We take k bounded from below or from left, so that we can apply the theorem. So we say that so then k is n malleable if again psi et al. Fibrant replacement G satisfies the following. So it's very similar to the definition. So again, we have to fix data. So for every we fix y g in h prime, then we fix just a system of variable with which has less than an element, and then we fix now something slightly different than before. So I call this 3 prime. So so instead of taking a relative hypercover of y, where we add with formal variable t, now I just simply take a hypercover v prime simply of y. So this will be a relative étale hypercover. So, and for all these data, I want that dot plus k g of v prime formal variables is acyclic. Okay, so as I said, it's really not surprising, and maybe I say one word. So this follows from the previous theorem, because of and induction. So we argue by induction on n. So I want to prove this at level n. So by the induction hypothesis, I know that k is n minus 1 malleable, and hence it will be almost n malleable. And so we need to go from almost n to n malleable. And if you look at the definition, you see that you only need to somehow to treat the case where v somehow covered the whole thing. But since our scheme are essentially Henselian, I mean, so this v, so the yt, this is a Henselian scheme, right? Since y is like a point, so every étale cover somehow is of this form, is obtained in this manner. Okay, so. There is a variant which I will not discuss really, which is slightly harder to prove. So the variant is that the same is true if 3 prime is replaced by 3 double prime, which is the following. So where we ask, so instead of taking any relative hypercover, I take somehow the finer one. So we ask that v prime y dot is again a relative hypercover, relative étale hypercover, with the condition that OVD are algebraically closed field. Okay, so I sometimes, maybe you can call this a relative, I don't know, algebraic closure if you want, or hyperclosure. So why this is harder? Because you see here you have the choice of taking any relative hyperhyperbola. For instance, you could take y itself, and here you have no choice. There is essentially one such gadget. Okay, and in fact, it's not even clear that there is one. I mean, there might be none, in fact, but one proved that there is one, and in fact, exactly one. Okay, I mean, maybe I should say why it's not clear that such a thing exists. It would be clear if I would ask, instead of algebraic closed field, I would ask something like, I don't know, a direct sum of algebraic closed field in some sense. I mean, direct sum may be indexed by a profinite set. This will be clear. The fact that that you can achieve a closed field is not clear. But on the other hand, this is important, in fact, that one has really one field because of the following corollary that I will state now. By the way, I should have said this. I mean, I'm always working with rational coefficient, but let me just say that that here Q coefficient is important. Before it was not, but for this variant, it's important to have. So here's a corollary that if you take k prime, 2 n malleable presheaves, complexes of presheaves, of Q vector spaces, then their tensor product is also malleable. And here's very quickly the proof. So it follows from this variant. So yeah, I mean there are two remarks. So here, so one remark is that so if V prime as in 3 double prime, then V prime T some D so GT is a point for the psi étale topology. Okay, so because it's strictly Einsteinian and formal, so it's and so in particular you don't need to speak about to check the condition. You don't need to take a replacement, a psi étale replacement. Yeah, so just take your k and you evaluate, and you want to show that the total complex is acyclic. And so what we do, we take this thing. So the point is that if you evaluate this here, then you get. Yeah, I mean, I should say that. I mean, it's a point because I mean, and it's important to know that V is also a algebraic closed field, not as I said before, sum of algebraic closed field. Right. So this is just a tensor. I mean, one show that this is a tensor product of the evaluation. Okay, and since these two guys are acyclic, by hypothesis, it's also true that Sorry. So I assume that k and k prime are malleable. So which means that the totals. So I have put dot plus. And one has to show that there is such an equivalence. It's not an isomorphism. I'm just saying that there is that these two complexes are quasi-isomorphic. Or maybe not. I don't know. But it's true that. Maybe I should do it. Okay, this is not true. So it is true that if I put dot without the plus, these two things are isomorphic. It's like for when you have a simplicial group. Take two simplicial group and the tensor product. You take the tensor product and then pass to the diagonal. Take associated complex is the same as taking first associated complex and then taking tensor product. This is called the I don't know which isomorphism. Eilenberg maybe something. Eilenberg, Zilber, Zilber maybe or something. Yeah, I don't know. It's a classical fact that, yeah. So one has to check. I mean, it does not work. It does not apply immediately here because we are working with semi-simplicial objects. One has to check that this is still available in this context. That the total space of this is the tensor product of the total spaces. But then if this is true, then you are done because the dot plus is really the cone of a map from k tensor k prime at v minus 1. And so it's also true that on v minus 1 we have this isomorphism. So all right. Okay, so why? So let me maybe say. So the main application of malleability is via the following proposition. So this is why we are somehow interested in this notion, because it implies the following proposition. So same hypothesis as before. And n malleable. So I assume that k is n malleable. And then we do the following. So we fix the following data. So we take foliation that I assume to be diff smooth with finitely many generic points. Take a system of variables. We don't assume a priori that it has less than n elements in it. Then C. I take an open subset, pro-open subset of so eta x. This is a generic. This is like the processing of dense open subset in X with formal variables. And I think this U will be a pro-open subset. Okay, and I assume that the dimension is bounded by n, dimension of U. And finally, yeah, that's it. So, and of course, I assume that I can evaluate my k on U. Okay, so. Okay, then the natural map from the étale foliated topology. And so for the psi-étale topology of U f with value in k is isomorphic to the foliated homology. Okay, so in some sense, if you are malleable, which is also not so surprising. So from the definition, if you are malleable, then you are close to being CFT fibrant. Of course, it's not the same, because I mean this kind of maps, this kind of isomorphism really depends on the fact that you are taking some nice foliation or profoliation. It will not work for a general thing a priori. Okay, so but this is the idea. So being malleable is really some kind of like being fibrant for the FT topology. So I want to give the proof of this because it's maybe illustrate a little bit the techniques. Yeah.
And then the whole commodity.
Yeah.
But it's not bound.
I mean, it's a complex, so I don't know. I mean, there's no. So the complex is bounded only from the left, but a priori, it's unbounded from the right. If you have a single sheaf, then this would imply that the cohomology CFT has bounded, but. I mean, yeah. Okay, so here's the proof. So we do, of course, induction on N. And so by a standard argument, using excision, we reduce to show that the cohomology, so it's the same, so the same thing that you want to prove is true, but in a special case, the case of you take the generic point of x, you add the formal variables. And here, of course, then you need to ask that that T is smaller than A. It will not be the same x and the same T, right? So somehow x will be probably the residue field at some point of u, okay, and then T will be some local parameters at this point. Okay, so but we reduce to this case. Okay, so yeah, some kind of excision argument. Yeah. Okay, so we can assume that that K is C eta phi bot. And we fix a CFT phi bot replacement. All right, so this guy computes this guy, that compute this. And so what we want to show is that the map K to K prime induces a quasi-isomorphism when evaluated at something like this. All right, so we also fix this gadget that I have introduced some time ago. This is called so an FT universal hyperenvelope of XF. Let me remind you what this is. So let's assume that X is irreducible. Then X prime will be essentially like the algebraic closure, the spectrum of the algebraic closure of the generic point of X. This will be like a so some kind of a pro object consisting of hypercovers, of generic hypercovers, and then the condition is that in each degree this guy has no further extension, is differentially closed in some sense. Okay, so this is a point in the CFT topology. So we fix such a thing. Okay, so now we consider the following square. So we have K, and so of course I should say this. So we are left to by Galois descent, if you want, we are left to treat this case. Okay, it's a small argument by Galois descent. We reduce to show this isomorphism. Okay. Now we look at the following square. I don't put the foliation anymore. It's called 1 dot and the same thing with K prime. Okay, my goal is to show that this here is a quasi-isomorphism. Okay, and so what I will do, I will show, of course, that 1, 2, and 3 are quasi-isomorphism. Okay, so, right, so let's see. By hypothesis, I know that K is malleable, and yeah, because of this, so since K is in malleable, this implies, essentially by definition, that one. Sorry, is there? Oh, I think I have a problem with the notation. Oh, is this correct? No. That's sorry. Since K is malleable, then one is a quasi-isomorphism. Okay. So essentially, this is because Q is an H. Essentially, or at least is the constituent of the process system U belongs to H. Okay. 2 is also a quasi-isomorphism. And this is because QD is a point for the FT topology, for CFT topology. And since K to K prime is a CFT local equivalence, it induces a quasi-isomorphism on every other point. So this is fine. So we are left to check 3. Check that 3 is a quasi-isomorphism. And so by induction on N, plus the previous theorem, we know that K prime is almost malleable, N malleable. And so, as a consequence, 3 will be, so maybe I'll write it like this. 3 dot is a quasi-iso. So what is 3 dot? It's the same thing as 3 where you put the 0 here. Okay, so maybe I write it. So prime, x prime, 0 going to dot. The quasi-isomorphism. Okay. So now since K prime is Sini-Snevich vibrant, we have these so-called Meyer-Vitor squares or excision squares. I maybe write it only for x. So so we have this homotopy Cartesian squares. Okay, and so remember, I want to show that and so similarly for Q, I want to show that this map here is a quasi-isomorphism. I know it here, and so to conclude, it's enough to do it here and here. Okay, so enough to show that. So maybe I do it for one of them. It's really the same x prime t. As a quasi-isomorphism. Okay. And now this is somehow something. I mean, this is the difference with formal variables or just polynomials, is that I can introduce. So let's call H this just simply hom an. So it's called an. This is spectrum kt. K prime. So I can introduce this new new sheaf, and I mean I could have done this also with formal variable, but when done with this, we know that H is still CFT5. I would not. I mean I could not conclude this if I put formal variables instead of polynomials. But with polynomial, I can still say that H is C5, and I'm left to show that H evaluated at x prime going to H evaluated at Q is a quasi-isomorphism. But now this is okay because H is fibrant and this is generic hypercover. Then I can conclude. Okay. All right, so now let's give some examples and application of this notion. So I first introduce a definition. So which concern F, a complex of pre-sheaves on smooth varieties over a field. So let also F prime be an étal fibrant replacement of F. So we say that say that f satisfies the formal Meyer-Weitoris property, which of course I will abbreviate by formal Meyer-Weitoris property. If the following holds. So for every local regular excellent K scheme X with closed point small x, the square f prime x to f prime x minus the point, f prime x completed at the point, and then f prime of x completed at the point minus x is homotopically Cartesian. Of course, I hope you understand. So I have to tell you, of course, how I evaluate f at such a scheme, which is a priori not a smooth variety. Yeah, of course, I do this by writing the scheme in an essentially unique way as a limit of smooth varieties. So there are known examples of f satisfying this property. I'll just give some of them. So, example, so if A is commutative group scheme, so I don't know if this is true in characteristic P, but in characteristic 0, I'm sure this is true. So we take a commutative group scheme, then A is, so A satisfies, or really the presheaf represented by A satisfies the formal Meyer-Weitoris property. So this is somehow the only example that I care about, but it's also an interesting source of example given by So if you take K, which is A1 et al. Vibrant, so if you want a motivic sheaf, then K satisfies also this condition. At least the proof in this case, it's an easy consequence of Popescu's theorem. I can deduce from this. Okay, so here's this theorem. So first examples of malleable presheaves. So take F, a complex presheaves on smooth varieties satisfying the formal Mayer-Vietoris property. Then G upper star of F is malleable. So I need to tell you maybe what is G upper star of F. So G is this morphism of site, if you want, from smooth, for instance, smooth foliation over K to smooth varieties given by just X with the coarse foliation. Okay, so it's a natural extension of a presheaf on smooth varieties to a presheaf on smooth foliation, smooth foliation. So this is somehow a source of examples of malleable presheaves. So I can sketch the proof of this. In fact, it's a consequence of the following lemma, which is in fact interesting for its own sake. So I will not prove this lemma, but you will probably imagine that this property would imply this lemma. It's quite it's not such a surprise, I think. So same hypothesis. So F satisfying formal Mayer-Vietoris property. Then for every R E diff smooth, say with R excellent, maybe regular. We have that the étale cohomology of R with values in F computes the psi étale cohomology of R mod E with values in the inverse image. So it's not so surprising because you see the difference between psi étale and étale is essentially given by this kind of completion. And so we have asked our F to satisfy excision for this kind of square, so it's not so surprising. Yes?
The definition of malleable is n malleable for all n?
Oh, yeah. Sorry, I did not say this. Yeah. So malleable is for all n. Yeah. Write it here. So let me explain the proof of the of this theorem assuming the lemma. Okay, so proof. So again, we argue by induction. So we prove that it's n malleable for every n. So induction n, and by this theorem I've explained today. So we need to check that G upper star F is n malleable, assuming it is almost n malleable. Okay, so we fixed G CFT C et al. Fibrant replacement of G upper star F. And so we need to evaluate G at something like this. If you remember the notation, we want this is our goal, basically. Okay, to check that something is malleable, assuming or by induction there is so it's actually one needs to check this only. But since I know that it is almost n malleable, I know that this is true if I put a 0 here. So if I remove the special fiber, this is acyclic. This is okay. This is, we don't know. But then I can compare these two things and use excision, so to reduce to enough to treat the case of G polynomials instead of power series. Okay, so we need to do these two cases. And more generally, show that. So more generally, showing that, or let's maybe just do one case and then say that the other is the same. So I do the case of polynomials. Okay, so now comes this lemma. So by previous lemma, it's enough to show that f b prime t dot plus acyclic. Here I'm assuming that f is et al. Fibrant, which is okay. All right, so why this is true? Because this is this guy is excellent and smooth and regular. Okay, but then so setting H to be R hom et al. AN with value in F, we are reduced to showing that H is acyclic. Okay, but now H is a sheaf, or is a complex of pre-sheaves on smooth varieties. This is I'm thinking about this as a I'm thinking about each v prime d as a limit of smooth varieties, and again it's a fact that this co-simplicial, so this semi-simplicial gadget is actually can be written as a limit of et al. Hypercovers. So it's not étale in the usual sense. So it's not étale in the sense that the morphism are étale, but its morphism will be smooth, but it's still an étale hypercover. Okay, I don't know if this is clear. So, I mean, the definition of an étale hypercover is you ask that. Let me do it for this guy here. Vd to cosc maybe d minus 1d is an étale cover, right? But you could ask also it is. I mean, it could be just any map which is an étale cover. Okay, so it will be of this shape. I mean, the map will not be étale. They will be actually smooth and have maybe large dimensional fibers, but there are still covers in the étale topology. Okay, is this clear? Yeah. I mean, yeah, they are actually generic étale hypercovers, but okay, doesn't really matter. Okay, so this implies that this guy is acyclic, okay, because H is fibrant and étale fibrant, and this is as good as an étale hypercover. Okay, so one can construct more examples out of this one. So make it a remark. So if you take some bunch of complexes, pre-sheaves, and smooth varieties, satisfying this formal Meyer-Vitorius property, then of course G upper star f1 Fn is malleable. So here, of course, here I'm with rational coefficient, and maybe of course I'm assuming that my complexes are bounded from the left. And this is simply because I know that malleability is stable under tensor product. Okay, it's interesting to note that if you that the tensor product of two complexes of pre-sheaf and smooth varieties satisfying this condition do not a priori satisfy this condition. Okay, so the condition of having this formal Meyer-Vitorius property is not stable under tensor product. Okay, because it's about the Cartesian square, and tensoring to Cartesian square destroy the property of being Cartesian. Another interesting example. So maybe which is not of this form. If you look at the sheaf of differentials, so this is omega I is malleable. So here it's the good one somehow, the one that takes into account the foliation. Okay, not the one that I restrict from smooth varieties. Okay. So this is malleable, and how do I see this? So proof. Malleability can be checked on the small site. I mean, this is not okay. It's not maybe very precise what I mean by this. So I mean, you want you try to check that your thing is malleable. You fix your data, and then you are just working on one small site. And if you fix a small site, then this guy is just a direct sum of copies of O. Okay. And then you can use the case of O that we know, because it's satisfied by Tories and so on. Okay. Here's maybe just a corollary of this. Is that so? If X is smooth variety, then so I think this has. So I mentioned this before. But this is the ramp cohomology, and it's a bit unfortunate. But the only proof that I know is via this machinery. So here how it goes. So because of this fact, we know that the ramp complex is malleable. And so we can. So then, by previous theorem, I know that, or proposition, I know that the Fourier cohomology of X with value in omega is the same as the psi et al. Topology of X with value in omega. But this is also H star CFT X O star by the Poincaré lemma. And then again, by something I said today, this is also just H star et al. X omega. And for this, you need to repeat somehow this proof here. Okay, to reduce to something coming from smooth varieties. Okay. So now I can state somehow the main objective of this chapter, at least a variant of it, Ring's theorem. And you imagine why this is what you want. So we fix I alpha in this theta bar. So I go back to the notation before. So I just write rho instead of rho I alpha, the map from U bar alpha projection map. I fix some if you want to test pre-sheaf or complexes of pre-sheaves. On smooth varieties satisfying formal Meyer-Victorius property. And I let F be the tensor product. So, but by the way, I mean, this Fi will be, for us, will be O star later. O star, invertible functions, or GM, yeah. Okay, all right, so then the conclusion is that then one or every CFT vibrant replacement of roll-over star G upper star of F tensored with O delta omega, computed for the C-Nistelrooy topology, is malleable. Okay, so of course, obviously we are interested in this because this is what appears in the theorem that of last chapter. Right? So, and in fact, what would really be important for us is not really this statement, but the way we prove the statement, because it will give us more information about this object. So I think it's maybe a good it's a good point to make a break. Yeah. So I think I forgot to say something which is could be useful maybe to. Just a remark. Yeah. So I said that if you start with K, which is malleable, then we know that that the cohomology K will be with some nice foliation or profoliation computes the FT the CFT cohomology, right? So I think there was a proposition about this. A bit more precise. So here we had some pro-open subset in some maybe formal power series scheme or foliation. Okay. So what I want to add to this the following fact. So as a consequence of this, one deduces that if you take a CFT vibrant replacement of your K, then it will be also it's also malleable. Which is a consequence of this fact. Because to check malleability, we only care somehow about evaluating at nice foliation. Okay. So and in fact, so to prove this theorem, what we will do is we will construct a malleable sheaf, pre-sheaf, which is not the five-minute replacement of that thing. We will prove that this thing is malleable and CFT locally equivalent to that thing, which would imply that the CFT five-minute replacement of that thing is given essentially by the thing we have constructed. So in some sense, it's actually very similar to the proof I just gave of the computation of the foliated cohomology of O delta. So maybe I should. So it will be a baby case of the discussion that will come. So maybe it's good to make this clear. So let me also say a remark here. So the proof I just gave, the proof that is the RAM shows that shows two things. So shows or can be restated as follow. So can be restated. So first we check that omega is malleable, and then we use the fact that O delta is CFT locally equivalent, or let's write like this. Okay, equivalent to omega. And from this we deduce that, so it follows in particular that this thing is malleable. And so we'll do something really very close to this. To show that this guy is malleable, we will construct a variant of omega, which can be proved to be malleable by hand, I don't know. And then we show that this thing is equivalent to that, the CFT locally, which would give, in particular, it will give also a way to compute this thing here. Okay, and this is what will be really useful for us to have a good computational or a good model of this thing there. Okay, so I try to make this clear. I will not give any proof, but I will just try to make this clear. Okay. Okay, so I need a tool to be able to write down this complex that I just told you about, which is the analog of this omega. I need I need to discuss the notion of generalized direct images. So this some useful construction. So I start with some notation. So this is a general discussion that makes sense really in general context. I will do it in the context of foliation, but you can easily extend it to any context. Okay, so we start with a morphism of foliation. So it's just a morphism of foliation. And so this data, so which will be written, so TB morphism, which we write, or which we refer to as P star. Okay, so when I write P star E star, I mean this morphism. Okay, just a notation for. And so I can I will speak about P star E star foliations. What is this? This is the data of a commutative square. So it is a commutative imagine what it is. So x1, x0, p1, p0. Yeah, so you can speak about morphism of P star, E star foliation, and so on. Just maps of foliation. And we can also form categories. So I denote by, so for the moment I only consider this category, smooth foliation, E star, E star. So this is the category of these things. With some conditions. So we want such that x0, f0 is diff smooth. Of course, diff smooth as a p0, e0 foliation. And I want that the map to the fiber product is diff eta. Okay, and on this I have so I can introduce a topology. So I mean there are many different possible things, and we will see many of them. But for the moment, I will just introduce one topology, which might sound a bit weird, but or naive, but. This is what I need for the moment. So this is a topology Psi Misnevich star. I should maybe write it Psi Misnevich 1, but just maybe I stick to the notation I have on the paper. But so Psi Misnevich star topology is generated by families f star I of morphism of P star E star foliation was such that, so there are two conditions. First, I want that the f0I to be isomorphisms for every I, so it's the same base, and I want the family to be a cover. Okay, so it's not maybe the best definition, but as I said, this is what I need now. So yeah, so we have a maybe a morphism of sight. Smooth. For this topology, with no topology here. Yeah, and this is so I done this by P as the morphism there. And what does this do? So it takes an object here and map it to simply the fiber product. Okay, so the obvious functor. And so this induces a direct image functor, or C Nisnevich star, P lower star. Yeah, so whenever you have a presheaf or complex of presheaves here, you can take the direct image. And so remark, so this generalizes the direct image functor. The usual one, RP lower star. Maybe for example for the Nisnevich topology. So in which sense it generalizes? It does in the following sense. I would maybe just say it already. So if you have a complex of presheaf on smooth foliation E0 P0, you can extend it here just simply by saying that when you evaluate at x star, f star is like evaluating at x1 f1. Okay, if you do this, then when you apply this functor to this complex of presheaves, you get the usual direct image. Okay, and so this construction somehow allows you to speak about the direct image for a more general class of presheaves. And so we will see examples of complex of presheaves which lives here but do not come from one on smooth foliation over P1. Okay, so I need this construction. Okay, so I think I can maybe now give you. So I can start maybe discussing or constructing this complex of presheaf that I need. So from now on, I'll take P star to be this thing here. Okay, so P star will be a diagram of, so this will be a diagram of K star schemes. And so it makes sense to speak about smooth foliation over this diagram. So we have we have a morphism of sight P smooth foliation P star with indexed by this thing. And this goes to the usual thing that we were considering before. Okay, so it's and it allows to speak about somehow generalized direct images. Okay, so I start by describing a complex of presheaves on this category here. So I start with a lemma. So which I will not prove. It's maybe it's a nice exercise if you want to try to do it. So it's a lemma about a module with integrable connection. So let's say fix an object in the indexing category. And so let me say that there is unique up to unique isomorphism. There is a module with integrable connection that I denote by n I alpha, which lives on E alpha, which is of logarithmic type. And characterized by a universal property. As follows. So for every module with integrable connection, MIC alpha, there is a natural isomorphism between M tensored with N I alpha constant global section over E alpha. So this means the constant of this module. Okay, so the kernel of the connection. So it's isomorphic to things that to M log. So M log will be the largest submodule which is of logarithmic type in M. Again, constant global sections, but now it's on this foliation. E alpha remember, there is a natural foliation on these guys, okay, which is functorial in the indices. So, yeah. So what I'm saying here. So if you take M, you look at this at the largest thing of logarithmic type. You evaluate M at this foliation, then this operation is represented like this by just tensoring with N with this with a particular module. And so it follows from this description that this is somehow nicely functorial in the indices E alpha. So one can think about this actually as some kind of a diagram of module with connection on the various E alpha. So I will not prove this. It's really not difficult, and you can find the proof in the paper if you're interested. So yeah, I'll use this thing to construct the complex of presheaves that I need. All right, so let's take some place. So, as I said, I want to construct a complex of pre-sheaves on foliation over this PR, this P star, this diagram of K star schemes, P star. So I fix let x star E and P star foliation. Let's say n smooth for P star, and with a diagram, with this indexing category. Or even maybe let's be just let's fix the index object. Okay, so we can form the following diagram. So form the following. So we have x1. I have a map that I call px to x0, f0. This project to e bar alpha ai. We have map rho to ai. And then I fix. So you have this map that I have that we have seen before. I think E alpha 0, where alpha 0 is the initial map such that x1 to e bar alpha 0 factors through the open subset. Okay. Good. So with this notation, we set y x star f star to be the following. So we start with Rx, we pull back the sheaf, so the modulus connection, and I alpha 0. So remember we have these things, they live here. So for alpha 0 it lives here. I pull back to x1. Then I take a direct image, px, our star. But of course, one has to take a direct image in the sense of modulus connection. So what it means really is you have somehow, so yeah, you have to take. So maybe I put a word, a curly star, maybe like this, just to say that it's really you will be taking section which are in the kernel of the relative connection. Okay, relative for px. Right? So if you want, what you do, you enlarge or you somehow you decrease the dimension of the foliation by making Cartesian square with a discrete one, and then you compute section here, and then maybe taking global section along px. Okay, so this is the right adjoint of the inverse image. But everything is non-derived. This is very important. Everything is on the level of the H0. Okay, and then we have this, and then we take the logarithmic part of it. Okay, so this is a well-defined modulus convention, again of logarithmic type, and it's kind of it's functorial in x star, f star, and so on. And so then to get the thing that we want, we just now take the RAM complex. So then finally we set y dot evaluated at x star, f star. By definition, this is omega, the RAM complex. Of course, we are over x0, f0, values with values in this thing. Yeah, so this gives a well-defined complex of free sheaves on this category. And actually, it's also well behaved when you vary the index I alpha, so it's really on the big thing. And I should say that this is you see from the definition that we really use the fact that we have this map. So it's we use the freedom, this extra freedom that we have when dealing with these categories. So it's really, it will be really a generalized direct image construction. Okay, so with this I can now more or less close to the end of the lecture. So I state two facts without proof, really, or maybe with some small comments on the proof concerning this construction. Okay, so here's the first first fact, proposition. So there is an obvious inclusion of complexes from O delta omega to y dot. Of course, this guy here lives on, I mean, these two things live on different categories a priori, right? So this is on foliation over P star. This is on foliation over EA. Okay, so remember here. This is the thing that appeared in the previous theorem, and we were working over foliation on this diagram. This guy is constructed is on foliation, on star foliation, if you want, over this diagram. Okay, but of course, as I explained, whenever you have something here, you can think about it as something living here in the obvious way. So it's in this way that you have this inclusion. Okay. Moreover, this induces an FT, a CFT local equivalence as follow when we take direct images. So when I take R C Nisnevich, so maybe I write it like this. So C Nisnevich roll our star for any complex. So F will be again a test complex of presheaves, let's say it's on smooth varieties. So this induces a map like this. And this map is a CFT local equivalence. All right. So this is first fact. So I said I will not really prove it, but maybe it's just few comment. So this is not difficult, I mean, to see. I think this is, maybe I can try to just quickly. So let's see. If you want to compute the H0 of the complex Y at a foliation X star P star F star, then if you look at the construction, I think this is given by you have this modulus connection, and this is just clear, and you evaluate at x 0, and take constant vectors. But the way this is defined, it's clear that this is also just Rx upper star n I alpha 0, again constant vectors, but now over x1 f1. And so then there is the last isomorphism, which really follows. I mean, since I probably don't remember, and I also don't remember the definition of O tilde delta omega, but it's really, I think it follows from the universal property of these guys that you have this. Okay, so it has to go back to the definition that I gave last time of this. Use the universal property of these guys, and then it's really kind of an easy thing to convince yourself of. It's really okay. And the second part is not really difficult neither. It's again it's a version of the Poincaré lemma, of the foliated Poincaré lemma. Which is not also surprising. So since, I mean, we can think about Y as like some kind of the RAM complex, and that this is the H0, we are left to show that there is no higher cohomology for Y, and this follow using the Poincaré lemma again. Okay, so I will not say more about this proof. But somehow the moral of this is that it will be kind of easier to work with Y, because it's really it's very close. It's very closely related to the RAM complex, and in fact it will be easier to prove that this Y, or rather the direct image like this, is malleable, and somehow this is the next result, which I will not really prove. Since the proof is quite involved, but it's really again somehow using similar techniques as the one I explained today. So it's maybe not worth really going into it. Okay, so here's theorem. So notation as above. And we assume furthermore that that f is a product like this, and the fi's are satisfies the formal by Torres property. Okay, so then the conclusion is that R Psi-Nisnevich star P lower star G upper star if tensor Y is malleable. And somehow, really, the good thing here is that I'm not taking any CFT fibrant replacement. This guy itself is malleable. So this is really I think the main theorem of this chapter. And as I said, it relies on similar techniques as the one I just described today. Slightly more involved because we are dealing with somehow the direct image. So we need it relies on a criterion for checking that the direct image like this is malleable, and it's a bit involved. But so as a corollary, I just want to state that. So as a corollary of this thing, we get this result, which is somehow what we should maybe keep for next lectures. So the two complexes of pre-sheaves as follow. So the first one is P lower star O star tensored n time tensored with this complex Y. Everything is made Psi-Nisnevich star fibrant. I take direct image, and then later I make this Psi et al. Fibrant. This is one complex. The second one is same, but here I take rho lower star instead of P. O star insert M. Now I take O delta omega. Here I have to make it Psi FT fibrant, and then make the whole thing. Psi-Nisnevich. Psi-Nisnevich fibrant, and then make the whole thing not eta but FT fibrant. Okay, so we have these two complexes, and the claim is that they are quasi-isomorphic. Are quasi-isomorphic on nice foliation. And this is, of course, it's on smooth foliation over the diagram A. Okay, so it's followed from general facts on malleability I discussed today. Okay, if it's not clear, please ask. Okay, so it's followed from the fact that if something is malleable, then its FT cohomology can be computed using its Psi et al. Cohomology. Okay, and so this is this is a fibrant. This guy here is a fibrant replacement, is a CFT fibrant replacement of that thing here because of this theorem. Because of that proposition. That proposition tells me that here the second thing is a fibrant replacement for the CFT topology of the first one. The first one is malleable, so it's almost like it's already fibrant. So okay, it's really the two-step that I tried to explain today that in the proof or in the computation of the FT cohomology of O delta the fact that it coincides with the RAM cohomology. It's really the same story, just more complicated. Okay. So I want to end this lecture with making some recapitulation, just so that we know what we have to remember for next time. So this is the third paragraph. So as I said, somehow one of the next the next goal is really to get rid of foliation. So next goal is to get rid of foliation. And so somehow we already did a good deal of this, and so we still have to speak about foliation, but in fact about very simple one. So I make a definition. Somehow the idea is, since we don't need any more the foliated topology. So if you see, I mean, there is no foliated topology anymore. There is either the Psi-Nisnevich or the Psi et al. And in fact, both of them do not really require a lot of foliation to be defined. They restrict well, for instance, to the so-called category of excellent foliation that I will describe now. So we denote by X for K the smallest category of K foliation such that, so it has these properties. One, we want, of course, it contains the spectrum of the field, and we want stability by gluing, over open set, over opens. Okay, so if you have a foliation which can be covered by objects which are here, then it should be also here. Second. So I want that if y to x is a finite presentation morphism, and if xf belong to this category, then also the basic induced foliation belongs there. And finally, if xf affine and belongs to X foliation, Z inside X closed, maybe of finite presentation, then the completion also, the weak completion belongs to X fold. Okay, so it's the smallest category which is closed under finite presentation extension and completion and gluing and so on and so on. So and of course the object of this category will be called excellent foliation. Okay, so object, maybe I'll make a remark of this. So I have some space here. So remark objects of X fol K are called excellent foliations, and they will be denoted by, and they are denoted by just simple letters like that. So we don't have to put some other foliation because we want to think about these as coarse foliations somehow. Sorry. Should I erase the second or second? Okay, so as I said, it makes sense to speak about the Psi-Nisnevich or Psi et al. Topologies on exfoliation, right? Because if you have an excellent foliation, then any cover for this topology can be defined by cover which is given by excellent foliation. Another remark. So I will be sometimes writing this, and or even maybe S, and I think it's clear what this means. Okay, so it's just smooth, diff smooth foliation which are excellent over S. Okay, or even sometimes P star. Okay, so with this, let me remark the following: that the construction of this complex of Prisci phi, okay, of course, I mean I can restrict it to this category. So maybe I also say a remark. We can restrict this complex Y, and that's, in fact, from now on we only consider its restriction to smooth X fol over this diagram P star. Okay. And so also let me put a notation before stating the thing that we need to remember. So so we know what is an infinite suspension spectrum. I want to introduce a variant of it. I put a tilde here on it, and this is so on something. By definition, this is given by the following collection. So essentially, instead of taking T, I take O star n times. Of course, this does not make a big difference up to homotopy, up to A1 homotopy, since T is O star up to A1 homotopy. Okay, so it's just it's more convenient for what I want to do now. So we have the following theorem, and we only need to remember this for next lectures. So there exists a morphism of T spectra on smooth excellent foliation over K between the ramp complex and SG A1. So then the thing that makes spectra stable, then tot the bar, and then direct image for the étale topology, C étale topology, pi Lauer star. Remember, pi Lauer star is the map from A to spec K on R psi Nisnevich star, P Lauer star, sigma T infinity tilde of Y. That's everything. Okay, so I think I said everything I wanted to say today. So, any questions? Yeah, so this has, I mean, it involves only these excellent foliation, which are essentially, I mean, just completion of algebraic variety, or maybe successive completion of algebraic variety. So they are not so bad, but yeah, next time we will see also how to get rid completely of this completion also, so that we get something which is completely algebraic without any completion.